Jai Hind students, welcome to my YouTube channel. Students, the only person you are destined to become is the person you decide to be. I repeat students, the only person you are destined to become is the person you decide to be. What I mean to say is that it is entirely you. It entirely depends upon your ability to become as you desire for. Right students? So with that, let's begin today's session. In the previous session, we have discussed the applications of Ampere circuit law. We have completed the first two applications. The magnetic field at a point due to a long straight current carrying solenoid, as well as the magnetic field due to a current carrying toroidal solenoid. Today, the third and the last application of Ampere circuit law is to determine the magnetic field at a point due to a thick current carrying conductor. I repeat, thick current carrying conductor. Right? So, conductor, current carrying conductor, it's in the form of a cylinder, isn't it? This is suppose a current carrying conductor. Let us consider this to be the axis of this current carrying conductor, and let us consider the radius of this current carrying conductor is r, and this is the cross sectional area. Clear students? And let I be the current flowing through it. Let I be the current flowing through it. Now here I must mention, here I is considered to be the direct current, DC current. Now DC current, which is under consideration, it flows throughout the material of the body. It flows throughout the material of the body. And in the subsequent session, when we come across the topic of alternating current, then we will study that alternating current which we use in domestic circuits because it is much more economical in production. So AC current is used. So in the case of AC students, it flows only through the outer surface of the conductor. So that is known as skin effect. AC current only flows through the outer surface of the conductor. It do not flow throughout the body of the conductor. So that's AC current. Skin effect is there. But here we are considering direct current, that is DC current. DC current is the current which remains steady and which flows throughout the material of the body. It flows throughout the material of the body. Clear students? So here we are dealing with DC current, direct current. So we have to make use of Ampere circuit law so as to find out the magnetic field at a point lying outside this current carrying conductor, at a point on the surface of the conductor, at a point, at any point inside the current carrying conductor, and last but not the least, magnetic field at a point on the axis of this current carrying conductor. So these are the various cases which we will be discussing during this session, right? So let's consider P be the point. It is an arbitrary point lying outside, right? And let its distance from the axis be smaller. So case 1 is, we are dealing with the case when point P lies outside. That is, when smaller is greater than capital R. Clear students? So we have to make use of Ampere circuit law. So as to enable us to use Ampere circuit law, we have to consider some imaginary loop, isn't it? So taking point O as center and OP is equal to small r as radius, we will draw a circular loop passing through point P as shown in the figure. Clear students? This is the loop under consideration. Here we can make use of Ampere circuit law. Now Ampere circuit law, it states that closed line integral of the magnetic field, it is equal to mu naught times the net current threading through the loop. This is the loop and this is the current threading through the loop. So only net current I, it is threading through the loop under consideration. Clear students? DL, as you are aware, it's the elementary portion of the loop under consideration, and its direction wherever possible is to be considered along the direction of the magnetic field. So here magnetic field at a point is given along this direction. Suppose this is the point, here magnetic field would be like this. Apply this rule, so it will be in the anti-clockwise direction like this. So dl, if you consider here small elementary portion dl, its direction will also be considered along the same direction, right? So what's the angle between B vector and DL vector? It is 0 degree. Obviously it is 0 degree, right? So what we get is B dl cos 0. It is mu naught I. Still further, magnetic field at any point on the circumference of this imaginary loop being equidistant from the axis of the current carrying wire is constant. Therefore, it can be taken outside the integration. Now, integration of dl, if you integrate or if you add the small elementary portions of the loop, that will give you the total circumference of the loop. And this loop is of radius r. So, the total circumference would become 2 pi r. It's mu naught I. Therefore, magnetic field would be equal to mu naught I divided by 2 pi r. And this formula is valid when the observation point P lies outside the current carrying conductor. So students, this is the first result, right? This is the magnetic field at a point outside the current carrying conductor. Right students, I hope you have understood this article. It's very simple. Now case 2. Let's consider case 2. When point P lies inside, that is, small r is less than capital R. So, in case 2 we will discuss when point P lies inside the current carrying conductor. Like, suppose point P lies somewhere over here. So, this is point 2, this will be distance r. R is considered to be the distance of the observation point P from the axis of rotation. So here, if we want to apply Ampere's circuit law, then we have to consider an imaginary loop of radius r, isn't it students? So, applying Ampere's circuit law, what do we get? Closed line integral of magnetic field is equal to mu naught times the net current threading through the loop. I am talking about this loop of radius small r. What is the current flowing through this loop? Remember students, we are dealing with DC current. DC current flows throughout the body of the material of the body, isn't it? So, from this portion, through this cross-section area, the current would be somewhat less as compared to the case when the current flows throughout the conductor, throughout this cross-section area of the conductor. So, here suppose the current flowing through this cross-sectional area is I dash. Obviously, I dash would be less than I, isn't it? So, here the current threading through the imaginary loop under consideration is I dash. Now, what we do is, students, we need to represent I dash in terms of I. So, that can be done with the help of unitary method. It's pretty simple. Look, for area pi r square, that's the cross-section area of the original conductor, right? Current flowing is I. For unit area, the current flowing would be I over pi r square. Therefore, for area pi small r square, which is the area of this new circular loop, right? When point P lies inside the current carrying conductor. So, for area pi r square, the current flowing through this cross-section area is considered to be I dash. And it will be given by I by pi capital R square multiplied by pi small r square. Pi get cancelled. So I dash, it will be equal to I small r square divided by capital R square. Clear students? It's pretty simple. So again the angle between these two would be 0 degree. DL is the length of the elementary portion of the loop and it is to be measured along the direction of the magnetic field. So angle between these two is 0. So we get B dl cos 0, it's equal to mu naught. I dash may be written as I r square divided by capital R square. Again, magnetic field at any point on the circumference of this imaginary loop, which is being equidistant from the axis of the conductor, would be constant. So it can be taken outside. Integration of dl, that will give you the circumference of the loop of radius smaller, which is 2 pi r. It is mu naught I r square divided by capital R square. Therefore, the expression for the magnetic field at a point inside the thick current carrying conductor would be mu naught I r square r, a single small r would be left, divided by 2 pi capital R square. This is the expression for the magnetic field when the observation point lies inside the current carrying conductor, or small r is less than capital R. So students, these are two very important results, right? One more thing to be concluded is when the observation point lies outside, then you can see magnetic field outside, it varies with distance r like this, in this manner, isn't it? When observation point P lies outside, that is for small r is greater than capital R, it varies with the distance as 1 by r, inversely proportional to the distance of the observation point from the axis. While if the observation point lies inside the thick current carrying conductor, then magnetic field is directly proportional to the distance. So in this case, B inside, it is directly proportional to smaller. Rest all the terms are constant. So these results will be very useful while plotting graph showing the variation between the strength of the magnetic field and the distance of the observation point P from the axis of the conductor. Right? So these are, students, very important results. We need to discuss some other results as well. So there are some special cases left still. Now case 3. Over here. Let's do it over here. Case 3. Now students, suppose the observation point lies on the axis over here. Then what is the value of small r? It will become 0. So at a point on the axis, small r is equal to 0. So you can substitute the value of small r as 0 over here. So the magnetic field becomes 0. So magnetic field at a point on the axis of a current carrying conductor is always 0. This is the result which we have discussed during Biot-Savart law as well. So I repeat, students, again a very important result. The magnetic field at a point on the axis of a current carrying conductor is always 0. Right? Okay. Case 4. Look, here the magnetic field is 0. As the distance of the observation point is increased from the axis, the magnetic field, which varies directly as smaller, the magnetic field strength will also increase. At a point on the surface, it will be maximum, and thereafter, at a point outside, it will inversely be proportional to the distance. The strength of the magnetic field will keep on decreasing then, right? So, case 4 is magnetic field at a point on the surface of the conductor, at a point on the surface, that is when small r is equal to capital R. When the observation point lies somewhere over here, here small r would be equal to capital R. Right, students? So again you can make use of this result. When small r becomes equals to capital R, what do you get? We'll be left with B magnetic field at a point on the surface. It will be equal to mu naught I divided by, small r can be written as capital R, so one capital R gets eliminated. We'll be left with mu naught I divided by 2 pi capital R. This is the strength of the magnetic field at a point on the surface of a current carrying conductor. And students, this is constant maximum value. This is the constant maximum value. Clear? So you need to remember all the 4 results. I repeat, students, before we plot a graph showing variation of magnetic field with distance smaller, let's repeat or recall the entire thing, right? Whenever the observation point lies outside the current carrying conductor, then magnetic field is inversely proportional to the distance of the observation point from the axis of rotation, from the axis of the current carrying conductor, right? In case the observation point lies inside the current carrying conductor, then magnetic field is directly proportional to the distance of the observation point from the axis of the conductor. In case the observation point lies on the axis, then the magnetic field becomes 0. In case the observation point lies on the surface, then magnetic field becomes maximum. So here it is 0. It will keep on increasing, till its value at the surface becomes maximum. And thereafter, outside, if you keep on increasing the distance, the strength of the magnetic field will keep on decreasing, right? So let's plot the graph, right, showing the variation of magnetic field with distance smaller. So we'll make use of all the results which we have obtained mathematically. So students, this will be the graph. Suppose x-axis, the horizontal axis, it represents the distance, right? And the vertical axis, it represents the strength of the magnetic field. It represents the strength of the magnetic field. And the origin, suppose it represents a point on the axis, that is, this is the origin, this is point O. And let us consider this to be the surface of the conductor, thick conductor, like this. We are aware at a point on the surface the strength of the magnetic field is maximum. This is B max, and its value is mu naught I divided by 2 pi capital R. This is at a point on the axis, the magnetic field is 0. And from this point to this point, magnetic field varies directly with smaller. So it should be a straight line, like this. Magnetic field, it varies directly with the distance of the observation point from the axis of the current carrying conductor. And then, when the point lies outside, then it is inversely proportional to smaller. So the graph would be like this, inversely proportional. It will meet at infinity. So here B is inversely proportional to smaller. So student, this graph depicts the entire situation, all the cases which we have discussed, right? So we are over with the third application of Ampere's circuit law as well. I hope you have enjoyed this session, right? Do practice these articles. So that's it for this session. Do join me in my next lecture. Thank you.